All right, so let's continue on with our talk on magnetism. If you recall yesterday, I gave you a bar magnet. And I labeled a north pole to it and a south pole to it. And we talked about how a compass would line itself up with the field lines that this bar magnet creates if you were to bring that compass close enough. If you just were out in the middle of a field somewhere, then it would line itself up with Earth's magnetic field and along a field line pointing to the north or to the south, depending upon where you are. Remember we talked about field lines going out of the North Pole and into the South Pole in the intro to magnetism. A couple points I want to make out here. These field lines extend all the way through, just like this, and so they're continuous, and you could essentially think of it as a continuous loop. So it's not like electric fields where you have field lines going out of a north and ending somewhere if there was a negative charge somewhere close in that negative charge. So these field lines are all continuous and going through as such. Remember, they're three-dimensional too, so they come out of the page and into the page as well. So what would happen if we had a bar magnet and you cut it in half? So you just cut it right there. So then you now have a bar magnet that looks like this and a bar magnet that looks like this. And so would you have just a north pole here, and the whole thing would be north, and this would be south? It would not actually be like this. This would be south, and this would be north. They've searched and never really found a magnetic monopole where you just have one pole, north or south. You always have a dipole magnet. If there's a great episode of the Big Bang Theory where Sheldon thought he thought a magnetic monopole, and he thought he was going to win the Nobel Prize, but anyway, his friends fudged the data because they wanted to get rid of him because he's being so annoying. So anyway, long story. So what makes a magnet? Let's just take a look here. If you look at a magnet in the case of like a ferromagnetic material, if you just have it in random order, and I'll show you a demonstration of this in class, then basically all the magnetic fields are not lined up. But if you then were to subject it to a magnetic field, and sometimes they do get lined up with the magnetic fields of the Earth, and then the material actually gets sort of a magnetic domain. Some of them may be a little bit out of order, but if you notice, these are more or less going east-west in this case. And so then this would be a magnet right here. It would have stronger magnetic properties than, say, the one above it. So that's just called a magnetic domain. Just interesting. It's what I want you to know about magnetic fields. So this could be the north and this could be the south. You could reverse it. You don't really know until you measure it. So magnetic field lines, remember, are just like electric field lines, but they don't go across. They don't cross each other, and they can exert forces on things. So if you had a north pole here and you put it close to a south pole of a magnet, we know what would happen. You'd now have magnetic field lines going just like that, and that would be if that was a uniform. Doesn't this sort of look like two electric plates? Metal plates, and so you'd end up having a uniform field in this general area right here. Okay, so let's get to the big things here. Yesterday I mentioned about a current carrying wire. Now if you had a current carrying wire with a current I going in this direction, that we know that a magnetic field exists around it. Really quick, if you try this once on your own, but we can use a right-hand rule, RHR, to figure out the direction of the magnetic field around this wire. So let's just take a picture from right here. We're just going to talk about that part right there. And so we're going to use our right-hand rule, a very simple right-hand rule. We're going to put our thumb in the direction of the current. Now if I do that with my right hand, then my palm is facing, think about it, away from the screen. My palm is facing away from the screen. If I now curl my fingers as if I was to reach into the screen and grasp the wire, where my fingers go into the screen, and right as they start to come back out, my fingers are pointing out. That indicates that the magnetic field is coming out of the page. So I'm going to use a circle with a dot to indicate that symbol, that the field is out of page. Out of page. Circle with a dot. Out of page. And then on the other hand, if you continue your fingers wrapping around underneath the wire, in a two-dimensional space that we have here, it's going into the page. And I'm just going to use X's. Some people use X's with circles, but X's indicate into page. So as you can see, we've got a magnetic field that is going out of the page above the wire, into the page below the wire. Now I'm just going to erase all this, because you should have wrote that down by now. And I'm going to put another wire in the area right here. But I'm going to make its current go in the opposite direction. So this current is going in this way. And so now we have two wires, wire 1 and wire 2, and it's going in the opposite direction. So now if you put your thumb in the direction of the current, your palm is facing the page. So now, which way are my fingers going above it? Notice that they're going into the page. I use X's to indicate into. You should have wrote that down from the previous notes. I'll write it up here real quick. X equals into page. And then if you continue your fingers around, then they would be coming out of the page at the bottom. Now, take a look at this little interaction right here, right in the highlighted area. Notice that you have two magnetic fields, both going in the same direction. Well, that's like saying you have a north field of a magnet and north end of a magnetic, my fault, and you're bringing it up close to another north end. What do two north ends do, or what do two south ends do? These two wires would actually repel each other. So there'd be a force this way on this wire and this way on this wire. They repel each other. Now, can you imagine what would happen if I flipped wire number 2's current around and made it go the same way? And what do you think would happen? We'll talk about that in class. All right, so going onward, just to talk a little bit more about the basics of magnetic fields. Let's see. We talked yesterday about, I may not be able to get to a magnetism 3, but we'll try. Okay, so I got about 3 or 4 more minutes here to keep you in check here, and let's see, what were the equations that I gave you? I gave you F equals BI/L sine theta. Do you remember this one? This was for the force on a current carrying wire in the presence of a magnetic field. So this is I going that way. So this wire, let's just talk about it from right here to right here. This wire has is in the presence of a magnetic field, and because of that, it will experience a force on it with the magnetic field being B, and then the current being I, and the length of the wire between the two yellow parts right there. Now, but just think about it real quick. In yellow, I'll bring in another piece of wire. What if the wire came in? No, I can't really draw it, not perpendicular to it here. But what if it came in at an angle other than gosh, if it was coming from top to bottom, so I guess I won't be able to do that. That's what's hard about 2 dimensions. So then we had F equals QVB sine theta, and this is where if you just had a particle coming in, a good review again here, I'll put a third right up there. So here comes a particle, and let's use a proton today. And so here comes the proton, positive particle, and it goes in, and we know that this equation would get, if we know the charge of a proton, which we do, we can look that up, 1.6 times 10 to the minus 19th coulombs, times the velocity of the proton, and then times the magnitude of the magnetic field. That would give us the force acting on the proton, and that force will always be at right angles. So this will be the force perpendicular to it if it comes in at 90 degrees. It'll be a little bit less, but it's still going to cause it to go in a circular motion. It could actually cause it to go in a spiral motion as well, or a helical motion, I guess you could say. You could get like a spiral staircase out of it if it came in at an angle. We'll talk more about that as well. So then I wanted to talk to you about the magnetic field that exists around it. So this is all review, and remember it was B equals mu O I over 2 pi r, and where r was the distance away from it, and mu O was, if you recall, the magnetic permeability in a vacuum. So look that up, magnetic permeability in a vacuum. I'll highlight that, and it's in your book. Okay, so not too much more I really have to talk about here, other than let's just I hesitate to try to teach a lot of the right-hand rules, but I'm just going to get them into your head here. So how could we figure out, let's do this one. How could we figure out the direction of this force? Because remember, this formula gives us the magnitude. So how do we get the direction? Well, try it once on your own. Here we go. You ready? Take your hand and look like you're waving at somebody, but have your thumb sticking out, straight, perpendicular to your fingers. So just all fingers together, thumbs perpendicular to your fingers. All right, so your thumb is going to go in the direction of the current. Boom. Palm is now facing up. Okay? Now you're going to rotate your hand until the fingers go in the direction of, oh gosh, see what I mean? It's going to be tough. I'll tell you what, I'm going to stop right there because I'm going to have you start rotating. You're not going to be able to follow that. We'll talk about it. Okay? Let's wrap up here with a solenoid. And then we'll be done. I've got about a minute to talk here. In about 12 minutes, I'm going to make this. If you were to have a piece of wire, here's a piece of wire, and it was coiled like this. You see what I'm talking about? And then let's just let it go on like this. Now think about this. Each piece, and if the current is going in this direction, so that means that in here, the current is going up, and here it's going down. But if you look at that, and you use that first right-hand rule that I taught you, what we end up seeing is that you get a magnetic field created by all these wires that really looks very similar to a bar magnet. In this case, you would get, let's see, you get a magnetic field that would have the North Pole here and the South Pole here, and the field lines would be going through as such. So by using wire, we can create a very strong electromagnet. Oh, stop there at magnet. And we'll talk more about that tomorrow. So I'm going to stop at that. And really, we've covered basically everything. It's just I've really got to get you with these right-hand rules. And the only way I can do that is to have you in class with me, and we can practice them together. And with your good listening skills, we'll get that last part taken care of. So just to wrap it up, really you've got the formulas to give you the magnitude, and then we're going to talk about the right-hand rules to give us the direction. Okay? And that'll be it for this magnetism 2.